All right. So in the last class, I was talking about properties of stress, and among the things I want you to remember are that whenever we come up with any sort of a failure criteria, the criteria needs to be in terms of invariants of stress. I had said that there are three independent invariants for stress at any point. You can either take the invariants to be the three principal stresses, or you can work with invariants such as trace, determinant, trace of stress square. Amongst the most popular stress invariants are hydrostatic stress, von Mises stress, and the three principal stresses. And once you know the three principal stresses, I had also said that you can go ahead and estimate the maximum shear stress acting on any plane within the material. Okay. Now, right. Now, Now, in terms of stress, a couple more things I would like to cover before moving on to other things. So, all of you have been exposed to the concept of Morse circle, right? Now, what is the purpose of this Morse circle strategy? What do you use the Morse circle for?
It is used to find out the principal stresses.
So one of the purposes is to find out the principal stresses. So if you are given a stress state of this particular form, so let us say that you have an in-plane state of stress and the other stress components are 0. So you have sigma x, sigma y, tau xy, which means that if I take a small cuboidal element which is aligned with xyz axis, and if I draw the stresses acting on each of the faces, so what do I have? So sigma x is the stress which is normal to the stress which is along the, it is the normal stress along the x-axis on the plane with normal along x-axis. Tau xy is the shear stress. So the first index tells you about the normal, tells you about the plane on which the stress is acting. The stress second index tells you the direction in which it is acting. Okay. So over here, what we are considering is an axis, something like this, that this is x and this is y. So for the, right, so this is tau xy. So similarly sigma y is the normal stress along the y direction. Tau yx is shear stress on the plane with normal along y and shear stress acting along the x direction. Okay. So fine. So you have this sort of a state of stress, and what is, how do you deal, means how do you draw the Morse circle? So basically you have your x-axis. So this is your x-axis, and over here you show the normal stresses, and the y-axis you show the shear stresses. Okay. Now first you would mark 2 points on this particular axis. One is sigma x comma tau xy counterclockwise. So in this particular case, so fine. So in this axis, so this is the counterclockwise direction shear stress. This is the clockwise shear stress. So for x, as you can see from over here, tau xy is causing a counterclockwise moment. So fine. So you mark this point based on whatever is the magnitude of sigma x and magnitude of tau xy. And similarly, you mark this point based on whatever is the magnitude of sigma y. Okay, so this is sigma y, and then based on whatever is the magnitude of tau xy. Once you mark these 2 points, so these 2 points have to lie on the circle which we call as the Morse circle, and then wherever this Morse circle, so in this case this is the circle, wherever the Morse circle intersects the axis, so those are the principal stresses. So here this is sigma 1 and this is sigma 2. So based on this geometric construction, you can show that sigma 1 would be equal to this, sigma 2 would be equal to this, and tau max would be equal to this. Okay. Now, I had told you that in general, state of stress is three-dimensional, right? Now, if it is a three-dimensional state of stress, we can't really use this kind of a construction in order to find out the principal stresses and the maximum shear stress. But this is quite useful whenever you're dealing with in-plane state of stresses. Why do you think we bother about, means, does this look like a very specialized situation? The in-plane state of stress means 2D state of stress. Do you think this is very, means this is something that will never appear, or this is actually something which will appear quite often because of some reason?
Sir, it will appear because of some constraints if we look at
So can
something.
you tell me what is the reason why this is valid for quite a few problems?
Like for example, pressure vessels, like when sheet metal is involved.
Okay,
And
very good. So pressure vessel is an example. Whenever you're dealing with sheets and you're having in-plane loading, then automatically you will have this state of stress. What else? So if you take shafts, for example, and if shafts are subjected, what are the typical loads which the shafts should be subjected to?
Torsion.
They'll
Bending.
be subjected to torsional loads and
Bending.
bending loads. Okay, so what kind of stresses would they generate? So bending would generate normal
Axial.
stress, and torsion would generate shear stress. So for a combination of bending and torsion, you would once again experience a stress state of the type considered for Morse circle, and you can use these expressions in order to get the principal stresses and the maximum shear stress. Okay, now as I had told you before, for the design of machine elements course, we would only be concerning ourselves with linear elastic deformation, and that too isotropic linear elastic deformation. Let us spend a couple of minutes over here to understand the implication of each of these words. First, let's start with isotropic. What is the meaning of isotropic material behavior? You must have heard, if you must have heard these two words, right? So whenever we are talking about material behavior,
It
It behaves
directions.
without any restriction in direction.
so you can have two types, right? You can have isotropic and anisotropic. Okay, what is the meaning of isotropic and what is the meaning of anisotropic?
Sir, in isotropic, it doesn't depend on the direction, whatever
What doesn't
direction,
depend on direction? Hmm?
direction or geometry, whatever stress or
Sorry, Baba.
like what like it doesn't vary with geometry.
What is it? in your statement?
Material
Sir,
constants,
The material
Lami's
properties.
constant.
Material
The
properties we can say.
material properties are independent of the direction along which we are measuring the property. So what it means is, so let me add a sheet here. So what this means is, so if I take a material, okay, now name one material property.
density.
Sorry, name one material property.
Density.
Modulus.
So let's take Young's modulus. That's a material property. Name a few other.
Density.
Refractive index.
What is it?
Poisson ratio.
Poisson's ratio. What else?
Density.
The
What
Lami's
is it?
constants.
Loud and clear, please. I can't hear.
The Lami's
So
constants.
Lame's constants. Okay. Well, they are related actually.
Coefficient of viscosity.
Coefficient of viscosity. Okay, so these are all material properties. So for solids, for looking at the material behavior, we can take elastic modulus. If you are looking at thermal properties, you can talk about thermal conductivity, coefficient of thermal expansion, so on. So let us take properties like elastic modulus, yield strength, ultimate tensile strength. Okay, so some things which we very commonly determine. So what does it mean if it is isotropic? What it means is, so if I cut a specimen, so let us say I am cutting some flat dog bone shaped samples like this. Okay, so if I cut one specimen like this, so let's call this 1, and if I cut another specimen like this, if I cut another specimen like this, let's say 2, and if I am going to subject do a uniaxial tensile test on these specimen, and if I am going to plot, let us say true stress versus true strain graph, and if for both of these specimen I end up with the same behavior, then I say that for any value of theta, so let us say this angle between the two specimen is theta. So if 1 comma 2, the stress strain curve matches for any theta, then you say that the mechanical or stress strain response is isotropic. So then we say this is isotropic behavior. Okay, what is anisotropic? So now instead of this, so let us say I have different response. So this is true strain, true stress. Okay, and then I have some response for 1, some other response for 2. Then we say the behavior is anisotropic. Isotropic behavior. Okay. Now, when I looked at the elastic modulus, if I am looking at linear elastic material behavior, what kind of a quantity is the modulus tensor? So we know that for linear elastic, okay, before we come to this, let me go back. What am I doing? Right. So next, that was isotropic. Next, let us come to linear elastic. There are two words here, linear and elastic. So first thing is, we are saying that we are only going to concern ourselves with elastic behavior of materials. So why are we not considering plastic behavior? Why are we limiting ourselves to only elastic behavior of materials?
We don't permanent deformation of the of the design of the machine.
Very good. So we do not want any of the machine elements to undergo permanent shape change. When they are subjected to loads, we only want them to undergo elastic behavior. So what we are going to do is we are going to work with the assumption that behavior is elastic, and we will see when it will turn into plastic. We will not allow it to turn into plastic. Okay, so that is one thing. So behavior, we want it to be elastic, and based on this criteria, we will ensure that it is only elastic. Next, linear. Now, one thing to realize is for metals, the amount of elastic deformation which metals undergo is very small. What is the maximum yield strength that you have seen for steels? What is the maximum yield strength that you have seen for steels? What is the maximum yield strength? So I have discussed about a bunch of steels, right? I talked about low carbon steel, stainless steels, 4000 series steels, and 52100 steels. Amongst all these steels, after heat treatment, what was the maximum yield strength that you have noticed? Which of these alloys gave the maximum yield strength?
Low carbon steel.
Arey Baba, you are not there in any of the classes then. Like, which of the materials was being used in bearing application for rollers and raceways out of whatever I have just specified?
So 52100.
Very good. So 52100 steel was used for bearing applications. What was the strength of these steels?
So it was
Do you
very.
remember? It was very high. It was close to 2 GPa, if you remember. Even 4000 series steels, after heat treatment, they give you an yield strength of somewhere around 1 to 1.5 GPa. What is the Young's modulus of steel? What is the Young's modulus of steel?
200 GPa.
So E steel is around 200 GPa. Depending on the variety, there may be some maximum of 5% variation. But okay, so it is around 200 GPa. I have said, so sigma yield. What is the typical variation for steels? So sigma yield for steels. Okay, what is the range in which it varies? The lowest yield strength will be there for low carbon steels. Okay, what is the yield strength for low carbon steels?
Sir, about 200 megapascal.
So it varies from about 200 to 2000 megapascals, or about 0.2 to 2 GPa. So what will be the epsilon? Okay, so what will be the strain? So if I am looking only at elastic strains, okay, for steels, what will be the range? What will be the maximum elastic strain that I can allow it to undergo?
0.01.
It is, so epsilon elastic steels. So this is epsilon max elastic steel. So this varies from 0.1 to 1%. Okay, so this is the maximum strain that material can undergo. Now, in general, is means
Sir,
so these are small strains. Okay,
sir,
so
it should be 0.01 to 0.001, right?
what are you saying? 0.2 divided. See, 0.2 divided by 200 is how much?
Okay, so okay, fine.
So, so the deformation which the material undergoes when it is being subjected to stresses for metals is very small. So because the strains are small, uh, and we are interested only in elastic behavior, okay, so we can take the material behavior to be linear and elastic. Okay, now in general, if you look at the relation between stress and strain, okay, so stress and strain are second order tensors, and I had told you, see, in general, stress will be related to strain through something like this, okay, where this is the modulus tensor, okay, or if I want to write this in index notation, sigma ij will be Cijkl into epsilon kl summation over k and summation over l. Now, how many constants will this modulus tensor have? Each index takes values of 1, 2, and 3. So how many?
81.
81.
So
81.
this has 3 to the power of 4 equal to 81 constants. Okay. But then they are not all independent. Okay. Just from symmetry, you get rid of lot of them. But for a now what you can show is that for isotropic behavior, there will be only two independent constants. Two independent constants. Okay. There are many different ways to choose these two, but the ones which we normally choose, what are the two elastic constants that we normally work with? We work with one is the Young's modulus, and second one is the Poisson's ratio. We normally work with this. And in terms of these, okay, so in terms of these, what is the relationship for? So if E is Young's modulus plus nu is Poisson's ratio. What is shear modulus? What is shear modulus? Shear modulus will be E divided by 2 times 1 plus nu. So this is the shear modulus. And what is bulk modulus? E divided by 3 times 1 minus 2 nu. This is what it is. Just a second. Sorry. This 3 comes in the numerator. No. One second. No. Sorry. This is correct. Okay. So this is the bulk modulus. Okay. So if you know the Young's modulus and the Poisson's ratio, it is suffice to fully describe the linear elastic material behavior. Okay. So in general, so in the design of machine elements course, we will be assuming isotropic linear elastic material behavior. Why do we consider it to be isotropic? We know single crystals have some face-centered cubic, body-centered cubic lattice structures, which should give anisotropic behavior. But why do we consider isotropic material behavior? What kind of a microstructure do the metals which we normally use have? If you take a metal part, cut it, polish it, etch it, and look under a microscope, what will you find? So let us say you are looking at a region of 1 millimeter by 1 millimeter. What will you find under the microscope? Will it be single crystalline or polycrystalline?
Poly.
It will be polycrystalline, and particularly if you are looking at a specimen or a part which has been obtained using casting followed by hot forming process, you are going to find a random isotropic polycrystalline structure. So anyhow, so I spent quite a bit of time. So we are going to assume isotropic linear elastic material behavior, and for these kind of materials, relation between stress and strain is given by this kind of a equation. Okay. So the strain components epsilon ij, or let us look at it in matrix form. Epsilon will be equal to 1 plus nu by E times sigma minus nu by E into trace of sigma into identity. So this is the generalized Hooke's law. You are normally familiar with some relation in either tensile loading, shear loading, or pressure condition and all that. Those are all specialized relations. The the general relation between stress and strain for linear elastic isotropic materials is this thing. Okay. Now, fine. So under specialized cases, you can figure out what is the relation between stress and strain, and you can invert this relation. So earlier relation was strain in terms of stress. You can invert it and you can write stress in terms of strain. No issues over there. Now, until now, uh, you have learned how to determine the bending stresses and the torsional shear stresses, right? So what are the relations that you have learned? How can I get bending stress from the bending moment acting at a point? What is the relation for bending stress or normal stresses from bending moment?
My by I.
So I can write sigma is equal to my by I. I need to know the bending moment at that point, the distance from the neutral axis, and the corresponding bending moment of inertia. What is the relation for shear stress? What is the relation for shear stress? What happened? I think
TR by J.
most of you are sleepy.
TR by
So
J.
tau is equal to TR by J. So if you know the torque acting at a particular point along the beam or bar, radius from the neutral axis and the polar moment of inertia, then you can find out the shear stress. Now, stresses that you determine using these relations are valid under some conditions, and what these relations give you, okay, these are called nominal bending and torsional shear uh, torsional stresses. Okay, so the important word to note over here is nominal. Okay, means this is the minimum stress that is going to get generated. Later on in the class, I'll be teaching you about different features which result in increased value of stresses. Okay, these features are called stress concentrators. Okay, so you will get introduced to the concept of stress concentration. So you need to know the nominal stress and the stress concentration factor in order to find out the maximum stress which is acting at a particular point. So for example, in the case of bending, when we are using this formula, we are making a whole bunch of assumptions. What are the assumptions? We are assuming that beam is subjected to pure bending, material is isotropic and homogeneous, that's fine. Material obeys generalized Hooke's law, that is also fine. We are assuming shear strain is zero, or in other words, we are assuming Euler-Bernoulli beam theory, and we are taking beam to be initially straight, that is initial curvature is zero, axis of symmetry is in the plane of bending, and for this all this set of assumptions, sigma equals to my by I. Okay, all right, so this is about the concept of stresses and the material model that we assume in uh, design of machine elements. Okay, next I'm going to introduce you to the concept of design factor. So the next concept that you're going to learn about is something called design factor, or also colloquially referred to as factor of safety. Okay, and design factor will be denoted by n subscript d. It will be denoted by n subscript d. All right, next let us let us see as to what this is. Okay, now first thing to note is that there are several uncertainties whenever you're doing machine design. What are the uncertainties? So for example, anytime you are solving or analyzing a problem, I have told you earlier, you have to approach it from two perspectives. One is the material perspective, means with regards to which you need to know what is the strength of the material. Okay, and then you have to analyze it from loading, geometry, and resulting stresses perspective. So you determine the stress within the component, and then you look at the strength of the material, and you ensure that the stress does not exceed the strength of the material. Broadly speaking, this is what we do. Now, when we are looking at it from material perspective, what are the uncertainties? So there are several. There is always a certain variation within the system in terms of geometric features. Okay, so let us say you are analyzing a pressure vessel. Now a problem statement may read that you have a pressure vessel of 10 mm with 10 mm wall thickness. Okay, but then in reality it is never going to be equal to 10 mm uniformly everywhere. There will be a variation in the thickness. Now, in the same manner, if you are looking at material composition and properties, so let us say property of interest over here is yield strength and ultimate tensile strength. Once again, because of the way the material is manufactured, heat treated, welded, you can have a variation in the material property from place to place. Okay. And then there could be an means any material model you use is not perfect. There is always some deviation from the material model. Then theoretically you are computing some stresses within the problem, but because of different stress concentrators, the estimated stresses could be different from what is actually happening. And then you can have over a period of time all components undergo corrosion and wear. And what do these two things do generally? They reduce the amount of material which is carrying the load, thereby increasing the level of the stress. So this right. And one thing I haven't said over here is you can also have an uncertainty in terms of the loading. Okay, so there is also uncertainty in loading. Okay, so for example, let us say that you are looking at a bridge. Okay, and then you need to and there is a train which is passing through the which is passing over the bridge. Now you know what is the static weight of the bridge, static weight of the bridge and static weight of the train. But then as the train is moving over the bridge, there will be dynamics. Okay, and because of the dynamics there will be amplification of the load, but you are not very clear what will be that amplification factor. So there is an uncertainty in the loading. So basically, to take care of all these uncertainties, we introduce this design factor. Now we can introduce the design factor based on deterministic methods and stochastic method. But in this particular course, I will be only using the deterministic methods. So what we are going to do is we will try to establish a minimum design factor which should be considered in the application. Okay, based on the uncertainties in loss of function parameter. Meaning, so let us say loss of function is based on permanent yielding, or loss of function happens when stress exceeds the yield strength of the material. Okay, so based on uncertainty of loss of function parameters and maximum allowable parameters. Okay, so let us look at an example, and through that we will try to understand what should be the minimum design factor or minimum safety factor we have to consider. Okay, only in this class I'll be calling it design factor, safety factor again and again, but as such within the course I will stick to the design factor terminology. Okay, so design factor is defined as loss of function parameter divided by maximum allowable parameter. So for example, it could be the ratio between yield strength of the material and the maximum von Mises stress. Okay, let us consider a simple example in order to understand what is this thing about the design factor. Okay, just a minute. So let us say that you have a structure, and the maximum load which is acting on the structure is known to within an uncertainty of 20%. What does it mean? So if someone says that I have a 10-ton force acting on this member, what it means is the force which is acting in reality could be varying from 8 ton to 12 tons. So there is a uncertainty of 20% plus minus in the load which is acting on the member, and the load causing the failure is known to within 15%. Okay, what does it mean? So let us say someone said that this structure fails at 15%, at 15 ton force. Okay, so they are using some measuring instruments and saying that okay fine, at 15 ton load this structure is failing. But when they are saying that, actually that measurement itself is inaccurate, and it can only be trusted to within 15%. Okay, so within 15%. Now what they're saying is, if load causing failure is 10 kilonewtons, determine the design factor and the maximum load that can be applied. Okay, so how do you go about solving this problem? So so what is the worst condition that can happen? So when they say that load causing failure is 10 kilonewton, in reality failure could be happening for 8.5 kilonewtons. Okay, this is the worst case scenario. Okay, so the minimum load for failure is 8.5 kilonewtons. Now load can be determined to within 20% certainty. Okay, so even though it is showing as some value x, in reality it could be 1.2 x. Okay, in the worst case scenario. So how do I get to know the maximum load that I can apply? So it would be x times 1.2 would be equal to 8.5, or x would be equal to 7.1 kilonewtons. Okay, so that is the maximum load that I can allow on that structure, and the design factor would be 10 divided by 7.1. So in this case it would be 1.41. Okay, so because of uncertainties in the material properties, in the loading, geometry, and a bunch of other reasons, we have to introduce the design factors in our applications. Okay, now consider another problem. Now over here what you have is, you have a column, and on this column uh, you are applying a force F, but then this particular force we want to apply it along the center, but you cannot apply it exactly within the center. So what is being said is that the diameter can be fabricated to within 1% of plus minus 1% of nominal direction. Support can be centered to within plus minus 1.5% of nominal diameter. Weight is known to within 2% accuracy. Weight of whatever is being placed is known to within 2% accuracy. And strength is known to within plus minus 3.5% accuracy. Okay, percent accuracy. Okay, now, all right. So within this problem, so like based on whatever information is given, you can show that I will be sharing this. You can do this as an assignment. I won't go through all the details, but you can show that the maximum compressive stress which happens will be equal to this applied load F divided by A nominal. So there is always this concept of nominal strength, nominal stress that we are going to use. So nominal is the specified value, but in reality that may not be true. So F divided by A nominal into 1.167. So indeed, if it is some static weight or force that you are applying, then the minimum design factor that you have to consider is 1.167 in this application. You can see that actually the numbers are not very big in terms of the accuracy of fabrication, or means the locating of the load. Okay, weight, strength of the material. But then you see, very quickly you are ending up with a design factor of 1.167. And in fact, if the load is not means if it is a weight instead of a force, if it is a weight which you are going to drop onto this particular column, then there will be a dynamic effect. Okay. And the force which will be applied on the column, force F, will be equal to weight W into 1 plus square root of 1 plus 2hk by W, where k is the column spring constant. Okay. So what it means is, even if you're going to drop the weight a few hundred microns from the column, even if h tends to 0, F will be equal to 2 times m nominal times g. Okay. So anytime you have an impact scenario, the force which will be applied will be at least twice of the self weight of the mass which you are placing on the column. So now, okay, and right. So what we will find is that, so based on all the criteria, you will see that in this particular problem, the design factor ND will come out to be 2.42. Okay. So wherever you have an impact like situation, you should consider a pretty good amount of design factor, as you have seen in this application. Okay. So this you can take it as a homework problem. I'm going to share the notes, but you solve this particular problem as a homework problem. Okay. All right. Oh, sorry. Okay. The last concept that I am going to cover today is that of stress concentration factor. Okay. Now let us go back to this example which I have covered in the first class. So what is this thing that I am showing over here? Do you remember?
So railway
PMA.
generators.
So very good. So this is permanent magnet alternator. Okay. What was this being used for?
Uh,
So this was 30 kilowatt rated. Okay. Used for what?
Generating electricity from the moving wheels of the train.
It is used for generating electricity. Okay. So it is used for operating the air conditioning. Operating air conditioning on trains. Okay. So what was the basic working principle of this PMA? What you have is, you have these pulleys. Okay. So you can see these pulleys over here. So these pulleys are attached to the wheel sets. Okay. So the pulleys rotate along with the wheel sets. Now there are two pulleys on the wheel set, and these two pulleys drive the two pulleys on the permanent magnet alternator. Now inside this casing over here, you have a stator and a rotor. So stator is on the outside and it is attached to the PMA, and rotor is the main shaft. Okay. Now rotor is the main shaft. Okay. So first question that we will be trying to look at is, why do you have many geometric features on parts? You will see that for many parts, particularly shafts, which are highly loaded, you have geometric features like fillets, holes, slots, threads, etc. So why do we use so many geometric features? And we will be looking at what is their role in stress concentration. Now, in order to understand why we have geometric features, you need to let us take a sectional assembly of the permanent magnet alternator. Okay. So over here, the part that we will be focusing on is this shaft. So this over here is the shaft. Now, what are all the things which are connected to the shaft? So you can see that this is the pulley. Now, how is the shaft connected to the pulley? How is the shaft connected to the pulley?
Bearings.
What are you saying? Shaft will be connected to the pulley through a bearing. Then what is the purpose of a pulley means?
Belt.
You connect the pulley to the shaft through a belt. Come on, guys. You can see the two parts, no? This is the pulley. Okay, so this is the pulley and this is the shaft over here. This is the shaft over here. How are the two connected? Okay, so you use two methods. Okay, first of all, what is the purpose? What are you trying to do here? What you're trying to do is you're trying to transfer the torque from the pulley to the shaft. Using the pulley, you want to rotate the shaft. Now, how do you do the torque transfer? You use two mechanisms. First is you have a taper here. Okay, you have a tapered section over here. So whatever is the taper on the shaft, on the pulley, you have the matching taper. So you first insert the pulley, okay, from the side, and then you place a washer. So this is a washer, and then after that you place a nut. You place a nut and you tighten the nut. What will the tightening of the nut do? What will the tightening of the nut do?
Ensure there is no relative movement between the pulley and the shaft.
Okay. And then what will happen at the contact between the shaft tapered surface and the pulley tapered surface?
The torque won't be transferred.
No, no. What will happen is you will end up generating contact pressure. Okay. So if you have so imagine like this. So you have a pulley, and then this pulley has got some, sorry, correct. This pulley has got this tapered surface. Okay. It has got this tapered surface. Now what you are doing is using the nut, you are applying some force F. So what should happen? So for this free body diagram to be complete, what should happen?
There has to be a force from the opposite direction.
There has to be a force in the opposite direction. Okay. So I need to have a force in the opposite direction, equal and opposite. Now, how do I get this particular force at the contact? So what will actually be happening is as I keep tightening the nut, I will be applying more and more force. And as I tighten it, what will happen is at the contact, I will end up generating what?
Pressure.
So I'll be generating contact pressure. Okay. So now this contact pressure can actually assist in, not assist, can cause transfer of torque. Okay. Because it can assist in transfer of torque. So that is one way torque is transferred. In fact, if you design your pulley correctly, without any key, you would be able to transfer your entire torque just using this contact pressure. Can you give me one example where this mechanism is used to transfer the torque? See, all of you have taken part in first year and second year workshop, right? Now,
The lead
in the
chuck is
CNC machining center, when they have to change uh, the tool, okay, what do? The tool has means the tool spindle has got this tapered surface, nice polished tapered surface. They insert it into the matching taper, and then they tighten it a little bit. That's it, and that will be able to transfer the torque. So anyhow, so you have this tapered surface. So using this nut, you will be able to transfer the torque. In order to use the nut, what geometric feature should you have on the shaft?
a thread.
You need to have a threading. So here you have a thread, okay, but this nut has to go to some location and stop. It should not continue moving around. So what should happen? So after some amount of threading, you are going to have a step, and then the taper will start. Now, what is this thing over here? This straight cut with this circular ends. What is this? What is this portion?
A key slot.
Okay, so this is slot. Sorry, this is slot for key. Okay, so you use this key along with the tapered surface to transfer the torque. Now, after this, you have a step, and then you have a step. So what do we call this kind of a geometric feature? So here you have these curved surfaces, right? What do we call them?
Fillet.
So you have a fillet. Okay, so every time you have a step, you have a fillet. Now over here, you can see something. What do you see here? So this is the,
Sir,
today everybody seems to be very amount of participation seems less. So this is what? This is a bearing. Okay, so how many bearings do you have? So this is one, this is another. So the shaft is supported on two bearings. Okay, now in terms of load, what are the loads which will be acting on the shaft? What kind of a load will the pulley exert on the shaft?
Torsion.
So it is transferring torque. So there will be a torque which the pulley will exert on the shaft. What else? Can the pulley exert the torque, means transfer the torque, if there is no belt tension? If you have a loose belt, will it be able to transfer the torque?
No.
It
no,
won't
sir.
be able to. So you need to have belt tension to be able to transfer the torque in a belt pulley system. What will the belt tension, what kind of load will the belt tension apply on the shaft?
Bending.
Bending moment.
Bending.
It will apply
Movement, sir.
bending, not bending moment. It will apply actually a load. Okay, a normal load. So if I look at my shaft, so simply put, what am I having? So these belt drives, so these belt pulley systems are applying some load. Okay, so let me call this F and F. But then this free body diagram is incomplete, right? What will provide the reaction forces? what will keep the shaft in place? So if the belts are trying to pull them in some direction, what is keeping it in place?
Sub bearings.
Bearings. Very good. Okay, so this you have the reaction load from the bearing. So now what kind of load system does this become? So what you have over here means this is called 4-point bending. Okay, so where in which portion does maximum bending moment occur? So from here to here you have constant bending moment and maximum bending moment. Now in addition to this, what else is happening? You also have a torque which is getting transferred. Okay, so now, so torque, let me represent it like this. So T and T. Once again, it is incomplete free body diagram. Where would I get the reaction torque? Where would I get the reaction torque? In the middle section from the alternator. How much will it be? It will be 2T. Okay. So this is the free body diagram for this particular problem. So what was the purpose of this whole thing? The purpose was to show. So if I go to the shaft drawing, okay, I will see there are a lot of geometric features. So I have threading here. I have a undercut and a fillet, a slot over here, again a fillet, a fillet, a fillet, a slot. So there are a lot of geometric features. It's not a simple plain cylindrical shaft like this. Okay, so uh, now whatever formula you have learned, my by I, tr by j, they will, are they valid for a shaft like this? Do you think you can use a formula like that for a shaft like this?
No, sir.
You will not be able to use it for a shaft like this. Those formula will give you something called nominal stresses. Okay, but then these geometric features means cause stress concentration. So let us see graphically what does stress concentration mean. Okay, so over here I am considering the following problem. I am considering a plate. Okay, and this plate is being subjected to, I am subjecting this to far field tension, far field uniaxial tension, far field uniaxial tension, and I am considering the case when sigma equals to 1 megapascal. What I am doing is I am taking a small hole in the plate. Okay, now what is happening because of the hole? So away from the hole, what is the value of the stress? Away from the hole, what is the value of the stress? Quick. I am applying the stress, right?
So 1
What is the
megapascal.
value of the stress away from the hole?
1
Sigma.
1
megapascal.
megapascal.
1 megapascal. I'm applying a normal stress or uniaxial stress of 1 megapascal. Now close to the hole, what is the magnitude of stress?
It will be 1 megapascal plus some stress concentration.
No guessing. I'm showing you a contour plot. What
Okay,
is the
so
magnitude of stress?
it is
How much is it? Can you see this?
3.02.
It is close to 3 megapascals. So a simple circular hole in a plate gives you a stress concentration of 3. Okay, so something to remember, that geometric features introduce stress concentrations. A simple example is hole in a plate, which gives you a stress concentration of about 3. So far from the hole, the maximum stress is 1 MPa. At the hole, particularly at the corners, uh, at this particular location, the maximum normal stress is, or sigma 11 max is close to 3 megapascals. Okay, there is a stress concentration factor of 3. Next, now there is a small catch. The as long as material is elastic, this whole stress concentration thing works well. But the minute plastic yielding starts, okay, what happens is that once you have plastic yielding, the stress level decreases. Okay, yielding reduces the level of stress. So for example, if I have a material with yield strength of 300 MPa, if I'm applying a far field tension of 250 MPa, then the maximum stress in my application is how much? It will be arrested at the yield stress value. Okay, so the maximum stress is only 301 megapascals. So you can see over here that it is only 301 megapascals. So the static stress concentration factor or static stress concentration is something we apply only for brittle materials. Okay, so something like ceramics, and uh, we will apply it only for brittle materials. And even among brittle materials, we will apply it only to those which do not have major inherent defects. So if you take, for example, gray cast iron has got graphite flakes in it. Okay, and these graphite flakes basically act like cracks inside the material. The stress concentration which graphite flakes would provide would be much higher than what any geometric feature would provide. So there is a concept of stress concentration, but the static stress concentration factor is used only for brittle materials, that too when they do not have any major inherent defects in them. Okay, next. So you are going to be exposed to two kinds of stress concentration factors. Something called static stress concentration factor, which will be denoted by KT, and a fatigue stress concentration factor, which will be denoted by KF. Now, the static stress concentration factor would come into play for static failure. Okay, so in terms of failures, we will be looking at two kinds of failures. So static and fatigue. Okay, so static means in an application for some at some point of time there was a lot of loading, and you want to know whether that load can cause a failure in the material. Okay, so that is static failure. Fatigue failure means you are repeatedly loading the material, and probably after 100,000 cycles or 1 million cycles the material will fail. Okay, so for these two situations you use different models. You do not treat them both as the same. So for static failure, we use static stress concentration factor, and for fatigue failure, we use the fatigue factor KF. Now, one important point is that KF, okay, will be used for all materials, okay, whereas KT is used for brittle materials only, and that too ones without defects. Okay, that is first thing. The second point I want you to note is that this static, so how do you get these stress concentration factors? You have two ways. Now, one approach is you can use finite element analysis. Okay, So if there is some geometry, some loading that you are subjecting it to, then you can use means formulae to get nominal stresses, and you can use FEM to get maximum stress, divide maximum stress with the nominal stress in order to get the stress concentration factor. That is one approach. But before computers came into play and before FEM was available, people were using these kind of graphs in order to get the static stress concentration factor. Now, the stress concentration factor is determined for a particular geometric feature and a particular loading type. So, for example, over here, we are considering fillets for circular bars. Okay. Now, the fillet, how is the fillet defined? There are three geometric parameters: capital D, small d, and fillet radius small r. These three parameters need to be defined in order to define the circular fillet. Then the graph is for this particular bar subjected to bending moment M. Okay. So for this loading and this geometry, the static stress concentration factor is given as a function of the fillet radius divided by the diameter of the smaller thickness bar, and you have graphs for different values of capital D divided by small d. In most cases, capital D divided by small d would be small only, it will not be very high. So this is another way. So you can either use the finite element method, or you can use graphs like this in order to get the static stress concentration factor. And remember, the graph will depend on the nature of loading, and it will depend on the geometric feature itself. So for example, there will be a different graph if for a fillet which would be subjected to tension. Okay, there will be a different graph for a cylinder with a hole which is subjected to bending moment M. So the stress concentration factor graphs will depend on geometric feature, and it will depend on type of loading. Now, even though KT is used only in limited places, we still it's a very important parameter, and we still determine it because KT is required in order to determine KF. Okay, the fatigue stress concentration factor, the definition is given over here. So what we do is we write fatigue stress concentration factor KF as equal to 1 plus KT minus 1 into Q, where Q is the notch sensitivity factor. Now, what can you say about the static stress concentration factor? Can it be more than 1 and less than 1? What kind of a property will stress concentration factor have? Look at the graph here. Where does it start from? The static stress concentration factor, where does it start from?
More than one.
It is always more than 1. It increases the level of stress. Okay. Now, so that is one thing. And then, so to determine the fatigue stress concentration factor, what are we writing fatigue stress concentration factor as? We are writing it as 1 plus KT minus 1 into Q, where Q is called notch sensitivity factor. Notch sensitivity factor. Notch sensitivity factor. So you use graphs like this in order to get notch sensitivity as a function of geometric feature. Now, notch sensitivity factor Q varies from 0 to 1. Okay, minimum value is 0, maximum value is 1. So what can you say about fatigue stress concentration factor in relation to static stress concentration factor? Which will be higher, fatigue or static stress concentration factor? Look at
Static.
Static.
again, think again. Q is always
Fatigue, sir.
less than 1. Okay, notch sensitivity factor lies between 0 to 1. It is never 1. It is always less than 1. Okay. So which one will be higher? Which one will
Static.
be higher?
Static.
The static stress concentration factor is always higher as compared to fatigue stress concentration factor, and static stress concentration factor is required to determine the fatigue stress concentration factor. So because of this reason, you should always know how to determine the static stress concentration factor. Okay. Yep. So that is it. That completes what I wanted to cover for today. I'm going to share the form. Give me a minute.
Sir,
Yeah.
so can you repeat the cause of static stress concentration?
Just 1 second. No? What do you mean? See, you have features like fillets, holes, slots, threading. You have all these kind of features on machine elements. An example is a shaft. Okay. Now, these features will cause a local increase in the magnitude of stress. The stresses will be higher than what you compute using this theoretical formula, which are valid for constant sectioned shafts. So a simple example is this thing. Okay. So if I'm applying a far field tension, nominal stress is sigma, but maximum stress because of the presence of the hole will be 3 sigma. So the stress concentration factor in this problem will be 3 when the hole diameter is small.
Sir,
Yeah.
so why is it negative near the hole?
Which one?
The
It's not. This is S11. No? It is not negative. It will come close to 0. I think that is just some interpolation. It cannot be. To my understanding, it will go to 0. It will not be negative sigma 11. It is just that. What do you say? During interpolation and then making of contours, it is showing some value, but as such, it will be positive only. S11. It will not be negative.
okay, sir.
All right, I have pasted the form in the chat. You can answer the questions based on what we have covered today. Please try to finish it by end of class. You have 15-20 minutes, so try to finish it within that. If you have any further questions, you can continue to ask.
Sir,
Yeah.
sir, why, like, I couldn't understand the point why you said that we shouldn't use the this thing for like we should only use the concentration factors for brittle materials.
The reason is for ductile materials, uh, once yielding sets in, yielding will set the maximum limit for the stress. It will not allow the stress to go beyond that. So I gave you this example now. So I have a sheet with a hole. I'm subjecting it to far field tension, but I'm applying a far field tension of 250 MPa. Okay, so I'm applying sigma equal to 250 MPa. Okay. Now what will happen is, so if this material has a yield strength of 300 MPa, then the maximum stress will get capped at 300 MPa. Okay. So it will not go beyond that. So there is no point in looking at there is no point in trying to determine this maximum stress in a ductile material using this static stress concentration factor, because that factor will be valid only if the behavior is fully linear elastic.